Hello everyone, I'm Jiaqi Gao, a fourth-year PhD student at Harvard University. Today I'm going to show you what does instant routing look like in the data center and how to improve the diagnosis process through domain-customized instant routing. This is a joint work with the University of Pennsylvania, Microsoft Research, and Microsoft. Availability and maintaining service level objectives are the biggest challenges facing cloud operators today. Operators are working hard day and night to keep the complicated system up and running. However, incidents can and do happen. Here is a table that collects the public incidents of the past 6 months in the Google Cloud and Azure. We can see that Google Cloud reports 69 incidents and Azure reports 21 incidents. It takes both clouds hours to resolve these incidents. Note that these are just public incidents. There are way more incidents under the cover. Now let's see the life cycle of an incident. Firstly, when the monitoring systems deployed in the data center detects the abnormal behavior or the customer is experiencing issues, an incident is created. The next step is finding the failing component, which equals to finding which team is responsible for the incident. This process is usually done by asking each team whether the problem belongs to its components. If so, then the team takes over the incident and apply the corresponding troubleshooting procedures. If not, then we need to find the next team until one team claims the incident. Just like when we debug a buggy software, rather than fixing the bug itself, we often spend most of the time finding where the bug exists. From our measurement, finding the right team is time wasting. Here is a CDF curve of the normalized investigation time when one or multiple teams investigate the incident. We can see that in the median, misrouted incidents takes 10 times longer to resolve compared with the incidents that were sent directly to the responsible team. So how to reduce misrouting? Previously, people tried to solve this problem with two approaches. Firstly, they build application-specific diagnosis systems, such as NetPro, which trains on each application, and DeepView, Sherlock, which explicitly encodes the application dependencies. But because there are too many applications in the data center, we cannot build one diagnosis system for each application. Another line of work tries to route incidents based on instant text description, such as a global instant routing system running in Azure, which is built on top of the NSA 13's work, NetC. But because it fails to consider the domain knowledge in each team, the accuracy is not high. Let's revisit our instant routing problem. We want to build an instant routing system that when an incident happens, it can summarize the engineer's domain knowledge and other resources, such as the monitoring data, and sends the incident to the correct team. Our first idea may be build a principled algorithm based on well-known rules and conditions over the set of inputs, but this can be extremely difficult given the multitude of teams, the magnitude of the data, and the diverse nature of the problems that occur in practice. Then another approach is machine learning. We can let a machine learning algorithm learn a pattern. There are many ways to build such a machine learning system. The simple solution would be build a huge machine learning algorithm that solves the problem at once. But we quickly found out that it is really hard to build such a single monolithic instant routing system with high accuracy. There are 4 problems. The first problem is the curse of dimensionality. Because the global routing system should consider everything, this large amount of information can easily result in a huge feature vector, but we don't have enough examples to train it. The second problem is uneven instrumentation. A subset of teams will always have gaps in monitoring, either because the team has introduced new components and analytics have not caught up, or simply monitoring is just hard. The third problem is the input is constantly changing. We may constantly experience stale components and monitors. The fourth problem is limited visibility. Because we're sitting at a global position, it is difficult to understand the appropriate feature sets from each and every team. So here we present Scout, a team-specialized gatekeeper. Instead of sitting at a global position, the per-team-based Scout simply answers the question, is my team responsible for the incident? So when an incident is created, the Scout can run local checks and intercepts or reject the incident based on the result. This design has 3 advantages. Firstly, each team only needs to maintain 1 Scout, so this solution is realistic and applicable. Secondly, our per-team-based Scout can easily leverage the team's domain knowledge, such as what are the team's responsible components, what are the monitoring systems deployed in the data center. Thirdly, each team can evolve its own Scout independently without affecting other team Scouts. To build such a Scout, we found there are three challenges. As we said previously, the Scout should leverage the monitoring data available. But since there are millions of devices in Azure, the amount of related monitoring data is huge. How to process them? Our insight is the incident itself can guide the investigation. The incident description usually can tell us the candidates of the affected devices, such as the affected servers, switches, and clusters. We can leverage the operator's domain knowledge and encode the device's naming convention through regular expressions and extract the potential devices out. After this step, we can find related devices monitoring data. Through this method, we can shrink our scope and collect a reasonable amount of monitoring data. Then, the next challenge is how to create a fixed-length feature vector out of the monitoring data. Each incident may have variable number of devices. The monitoring data also has mixed types. Some of them are time series, such as the temperature data. Some of them are event-based, such as the reboot event. How to summarize them together? Here, we propose a two-tier aggregation solution. In the device tier, for the time series monitoring data, we normalize the data and compute a series of statistics, such as different percentiles, average of the data, etc. For the event-based monitoring data, we sum the number of events during the incident period. After getting each device's feature vector, we summarize them via statistics such as percentiles and averages. So through this algorithm, we can build a fixed-length feature vector for each incident. After collecting the feature vector, the third challenge is which computation engine do we use? The solution we chose is a hybrid of a supervised learning algorithm and a statistical algorithm. For the supervised learning algorithm, we use the random forest algorithm. It learns based on the historical incidents and related monitoring data and has high accuracy on old or recurring incidents. Another benefit of the random forest algorithm is that it is interpretable. We can provide more insights to the engineer rather than just say yes or no. But because this algorithm is trained on top of historical incidents, it has low accuracy on new or rare incidents. So we use the change point detection algorithm to overcome this drawback. In a nutshell, the change point detection algorithm is able to detect the change points in a time series of monitoring data, and we believe these change points might be the cause of an incident. So then how to merge these two algorithms together? As we said previously, if the incident is recurring or common, then the random forest algorithm has high accuracy. So we can let the incident itself tell whether it is a new or old incident. The selector uses a meta-learning to identify new incidents. If the selector thinks it is a recurring incident, it will send the incident to the random forest model. Otherwise, it will call the change point detection algorithm. So at last, we can call the corresponding computation engine and get the classification result. Okay, so now let's revisit the overall design of a Scout. Given the incident description, the Scout uses the domain knowledge to collect the devices and find the related monitoring data. Next, the Scout builds a feature vector and assigns to the hybrid computation engine and returns a classification result. To evaluate the Scout's performance, we build a Scout for the physical networking team, which is in charge of each and every switch and router in Azure. We collected 9 months of incidents and randomly split them into training and testing set. For the baseline, we compare the Scout against the current incident routing system without Scout's involvement. The current incident routing system includes the engineer's runbooks, past experiences, and the NLP system we introduced previously. Here is a table showing the overall performance metrics: precision, recall, and F1 score. The baseline can achieve around 90% of precision and recall. And here is the result of a Scout. Compared with the baseline, the Scout can gain 10.3% on the precision and 5.8% on the recall. This 10% gain saves more than 20% of the total investigation time in 40% of the positive incidents. Due to the time limitation, there are a number of things we did not talk about. The first thing is the investigation of why incidents are misrouted. We also did not mention the design and evaluation of a Scout master that combines multiple Scouts and summarizes their results together. We also didn't talk about the series of extended evaluations. At last, we also wrote down the lessons we've learned from the deployment. Please check our paper for more detail. So, in conclusion, we show that incident misrouting is the main challenge for maintaining service-level objectives in the cloud. And we propose the Scout, a distributed team-specialized gatekeeper. We built and deployed a final Scout that can achieve higher than 97% precision and recall. Thanks for listening, and I'm happy to take questions.